Hi and welcome to today's class. It is the 25th of May and this is class 109. Today we're going to focus on loans and mortgages and something called amortisation. So let's talk about loans and mortgages. A loan is where you take out a sum of money and then you pay it back over an amount of time. Now, generally we have to pay back a fixed amount, and that is what we call amortized or an amortized loan or amortization, where the amount is fixed, and we end up paying back more than we borrowed, and that extra piece is our interest. And when we talk about mortgages, and it's probably something you hear the word a lot, but mortgage is a very special type of loan that we take out on a building, and most people have a mortgage if they've bought their own house. So the process of accounting for a sum of money by making it equivalent to a series of payments over time, such as arises when paying off a debt, so like a loan over time, this is called amortization. A loan that involves paying back fixed amount at a fixed regular intervals over a fixed period of time is called an amortized loan. So here we have two formulas. Now they're actually the same formula. This is what's given in your book and it's lovely. I really do like this as a formula. However, you're not going to have your book. Instead, you're going to have your log tables in your exam, and this is the formula that you have in your log tables. You'll find it on the very top of page 31. It's the very last formula that we use from the financial math section. It has A, which is the annual repayment amount, so that's how much you pay. Now, it doesn't have to be annual because like our other formulas, if you want A to be monthly, just make sure that your interest rate is monthly. P is the principal, so the amount of the loan. In this case up here, they've told it the mortgage. I is the interest rate, 1 plus I to the power of t. The t is the time, so in years or months, again, that t, that period, must match the period of A, the repayments, and the I, the interest rate. All over 1 plus I to the power of t minus 1. So there it is there. Okay, we're going to work through a mortgage example. So a mortgage of 250,000 repaid monthly, given an interest rate of 2.55% APR over 30 years. First thing that they generally ask us to do is to calculate a monthly interest rate. Remember we talked about APR, the annual percentage rate. That's given for loans and it's a legal requirement which will allow you to compare different loans from different lenders. However, with the calculation, because we're repaying it monthly, we need to understand what is the equivalent monthly rate. So what we do is we have 1 plus or the monthly rate to the power of 12. So whatever I invest at that monthly rate for 12 months should be the same as using the annual interest rate for 1 year. So remember, the opposite of power of 12 is the 12th root, and working backwards, I like to leave it in the root form as long as possible rather than decimal, and this works out as 0.210056%. Remember, multiply by 100 to get back to percent. So then we have this interest rate. So then what will be the monthly payment? So we're going to focus and use that amortization formula from page 31 of our log tables. So let's give this a go. So we have the loan itself, which is in this case a mortgage, is 250,000. We have our I is 0.210056, but remember we need that in decimal, so that is 0.00210056. And the time, it's going to be 30 years, however it's going to be paid monthly, so 30 by 12 is 360. So let's put that in to the formula and it looks something like this. Now, I use the square brackets. You don't have to use the square brackets. Sometimes I find students get a bit confused. It also helps us when we're doing other types of questions, figuring out how much the mortgage is, etc. So I use those square brackets and I put that all into the calculator as is. That 250,000 is multiplied by those square brackets, and we should get the monthly payment of €990.49. So a lovely little formula. I think it's really important to know when to use it because often that is the issue. Students go, but I just don't know when to use it. So if you're paying off a mortgage, and it's an amortized mortgage, basically what's going to happen is that amount that you pay is going to vary in what it is actually paying. So for example, any payment has a combination of interest and principal. Now, interest takes priority. So if the set amount, so in our case, we had 990 in the last example. So first of all, they work out how much interest needs to come out of that, and then the remainder goes for paying off principal. So often you hear people talking about they've paid back years and years of a mortgage, and they still owe nearly as much as they did to begin with because they've literally been paying so much interest. So when you make a payment, a portion goes towards paying off the principal and a portion goes towards paying off the interest. And it is the interest that takes priority. Remember that. As the principal outstanding reduces, as you owe less, then the interest will be less because the interest is charged on what's outstanding. So what it looks like is this. So the principal is in yellow and the interest is in that kind of dark red. So you can see now this is just a random 30-year mortgage of 200,000 and it's just looking at each year. So look how little principal is being paid off in the first few years. Like we're looking at about 2,000 out of a payment of 15,000, like such a small piece of that. So your loan, like they still owe 198,000 after year one, after paying 15,000 of a loan. And this is often what gets people quite upset about mortgages, a lack of understanding. But what happens is, and you can see it's nearly like an inverse exponential here, that we have this, the amount of the principal is getting bigger, bigger, bigger as they go. So let's look at doing what's called a schedule of payments for this particular example, like keeping this example. So a schedule of payment is to try and understand how that payment is broken down between interest and principal. So here's a table. I'm going to do 5 payments. So this is our same example. And if you take a look, we have the first payment and all the payments are set, like that doesn't change. The interest rate is set. So the outstanding principal at the start, so you owe the whole 250,000. So the first thing we're going to see is, well, how much interest do we actually owe in a month? So we calculate 0.210056% of 250,000. And we end up at €525.14. So that's the interest portion that has to be paid. And then we know that we pay €990.49. So to work out the principal, we simply take 525.14 away from 990.49. So that gives me 465.35 of a principal paid. So how much principal is outstanding? Well, we had 250,000. I've now paid 465 euro and 35 cent. So there's 249,534 and 65 cent. And we start the process again. So we figure out how much interest do I owe on that. Now, notice that the interest is a little bit less because the principal outstanding has gone down a bit. The interest portion has gone down, which means the principal portion will be a little bit more. So we lost just under €1. So we're going to gain that 98 cent back on the principal portion. And so on. So it continues. So we do see these asked on the paper. Sometimes they're usually laid out in a very similar way. This is quite a long, tedious task. And, you know, each line depends on the previous line. So there isn't really a quick way we could do these. However, there is a quick way they can be done. Not really something we could do in the exam because what we've used is Excel, but it could be any kind of program. So Excel is like a mathematical, a spreadsheet program. It's very much used for accounts and calculations. So boom, this is how it worked out. And like when I say seconds, yeah, no, it was seconds. So we've been able to create this lovely schedule very quickly. I've gone down to 20, but I did the full schedule over the whole term. And you can see here the interest portion going down, 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 and the principal portion going up, 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 up. But like after 20 months, Okay, so that's what 20. So we're just under 2 years. Like they have only paid about 10,000 back. So like if you think about that, that's 990 over 20 payments. So they've paid nearly 20,000, but they've only decreased by about 10,000, not even 10,000, 9,000. Like, and I suppose this is where education around loans and mortgages is so important, that you think you've paid back so much of your mortgage, but a lot of time you've just focused on the interest. Now, Excel is fantastic because it also allows us to visually see what's happening. So here is a beautiful graph similar to the one I showed you, but this one is specifically for our example. You can see that that top line represents that 990 that we pay every month. And you can see what's happening is over the course of the term of the loan, so 360 months, we have the interest portion going down, down, down. Now, this is a good example because we have about, we were just over 50% interest. So when I say, what I mean there is the payment, about half of it was going on interest at the start. And you can see how it comes down. But if you stick with it, it starts to go down a lot quicker. So let's look at an example. So calculate the size of the monthly repayments needed for a car loan of 10,000 if the loan is to be repaid over a 5-year term at an effective monthly rate of 0.72%. Okay, so we need to understand first P, the principal of the loan, and that's 10,000. Then we need to understand I, so it's a monthly interest rate of 0.72%, but remember we need that in decimal, so it's 0.072. T, it's a 5-year term, but we're paying it monthly, so it's going to be 60 payments. So these not annual payments, but in this case the monthly repayments are going to be 10,000 times 0.0072 times 1 plus 0.0072 to the power of 60 all over 1.0072 to the power of 60 minus 1, and that can all go in our calculator. And that works out at 205.84. So think about that. So when you pay back 205.84 per month for 60 months, you end up paying 12,350 back. So it costs you nearly 2,500 to get a loan of 10,000. And to understand the cost, the idea of cost of loans and mortgages, it's so, so important. Okay, so find the monthly repayments required for a mortgage of 150,000 based on an annual rate of 4.5% over 20 years. Now this is quite higher levels, well, they're all higher level style, but this is very, this is kind of the question we would expect, because it's not a simply plug in. So our interest rate, the problem is we don't actually know it, because 4.5% is annual, so we need to change that. The time is 20 years, but their monthly repayment, so it's 240. So the first thing I need to do in this question, and they didn't make it clear, and this is why you have to be on the ball and keep an eye out for the words. So step 1, we need to find the monthly interest rate. Interest rate. So how we do that is we say, well, look, if I invest something at a monthly interest rate or for 12 months, it should be the same as investing something at 4.5%, which is 0.45 for 1 year. So we have 1 plus or is equal to 1.045. To the power of 12, 1.045. 1 plus or is then equal to the 12th root of 1.045. So or is equal to the 12th root of 1.045, and then we subtract 1. Now, what I tend to do with these is I'll go to my calculator and I'll put that in. And in a lot of cases, they're quite small, and students get back a funny looking scientific notation, which kind of freaks them out. So in this case, what I will do, make sure that -1 is not under the square root. Now please make sure that -1 doesn't come out. I got a funny looking scientific notation. If you can work at scientific notation, great. If you can't, remember that's decimal. So if I multiply by 100, I get my percentage. So I multiply by 100 on my calculator and I leave it as 0.3674. I'm going to go 5 and I put in my percentage, and then I'll be able to do that conversion when I need to come along and do my I piece. So now we have that interest rate, we're going to put it as a decimal, so 0.003675. So I find that's a little bit easier for students just to do the multiplication, not mess around with the scientific notation and then change it back. Be really careful about listing or putting in your percentage sign when you have a percentage. So we have A is equal to P, which is 150,000. I 0.003675 bracket 1 plus 0.003675 to the power of t 240 all over 1 plus 0.003675 to the power of 240 minus 1. This is often split into two pieces in an exam question, so they would let you know how many decimal places to go to with that interest rate, so don't panic about that. Okay, if you want to pause and see how you get on with this, but do try put it into the calculator. Make sure you get as much practice with the calculator as you can in this section. When you put that into the calculator, we get 941 and 70 cents. So example 3, we were asked about deriving this amortization formula. This amortization formula is a fantastic little formula, and I always stress to students, if you have a loan or a mortgage, just go to that formula. It's such an easy little question. However, you don't have to use the formula. We could use the idea of a geometric series. I would already focus on the geometric series. However, in this question, they asked us to derive the formula. Now, to me, this is not a proof, but this is something that you would want to make sure how to do. And it would be good to practice it, but it's definitely not something you should be learning off. We're going to now look at how we would figure out that formula from just a normal sequence. This was asked on a paper. And it says show how the formula is derived. There is no formal proof for this. This is simply setting it up as a geometric sequence and working with it. A little bit harder than usual because it will all be in terms of letters, but let's give it a go. When a loan P, so that's our total amount, is repaid in equal repayments of amount A at the end of T equal periods of time, I is the periodic compound interest rate expressed as a decimal. That's really important. The formula can be used to find the amount of each repayment. Show how this formula is derived, and you may use the formula of a sum of a finite geometric series. So what we have is we have a loan here. Okay, so this is your loan, and we've taken it out, and it's P. And to pay back that loan, we're going to pay back A, and that is period 1, so that's T1. But when we talk about that A is actually going to be worth a little bit less when it comes back. That's called a present value. So because we're working backwards to that P, we're going to end up dividing it by 1 plus I. Plus T2, we're going to divide that by 1 plus I to the power of 2. So that's our term 2. Think of it as year 2. Think of it as whatever you want time period wise. And the last one will be 1 plus I to the power of however many time periods there are, which in our case we were told was T. So this is TT. So to figure out how do we jump from one to the other, we're multiplying it by 1 over 1 plus I. So that will be our common ratio for the geometric series. And we need to know two things. for the geometric sequence. Well, we need to know three things really. So our first one is a, the first term, which is a over 1 plus I. The next thing is or, the common ratio, which is 1 over 1 plus I. And the third thing that's really important that you know is n, which is equal to t. You then have to work with your Sn formula. So S, and we're going to do t in this case, is equal to a, so our first term, 1 plus I, times 1 minus or to the power of n, which in this case is t, all over 1 minus or 1 plus I. So that is our formula, and we want to take that formula and work it through to basically make it look like this. So notice that there's no S of t there. In that formula, that's going to be equal to P, the total amount of the loan. We're now going to take this piece here and work with it until we make it look like what's in the question. So the first thing I'm going to do to try to tidy this up is I'm actually going to multiply the top by 1 plus I and the bottom by 1 plus I. So that's the whole bottom and the whole top. When we do that, these cancel and the bottom line will look a little bit different. So what we get on the top line is a bracket 1 minus 1 over 1 plus I to the power of t all over. The 1 by 1 plus I gives me 1 plus I, and then it cancels with fraction minus 1. And that, remember, all equals p. When we do that, the ones cancel like this, and we get something a little bit easier. So I'm going to just bring this over here for a second. We end up with a bracket 1 minus 1 over 1 plus I to the power of t equals p times I. So I've multiplied both sides by I to get rid of that I in the bottom. I'm trying to figure out a on its own. So what we can do is a is equal to p times I divided by everything that was here beside a. So this whole bracket here. So we have 1 minus 1 over 1 plus I to the power of t. Now keep an eye on what we have, or what we want and what we have. So at the moment we have the p and the I, that's good, but we're missing a lot more. So what we're missing is a 1 plus I to the power of t on the top. So what we can do just to tidy this up a little bit is I'm going to leave the p I up the top. I'm going to break up this fraction because 1 to the power of anything is going to be just 1. So that gives me a 1 plus I to the power of t here at the bottom. And what we can do then is multiply the top by 1 plus I to the power of t and the bottom by 1 plus I to the power of t. And what we end up with here is a equals p I times 1 plus I to the power of t, and on the bottom we end up with, I don't have much space for my bottom line, but 1 plus I. I'm going to just give a little bit of space here so we can actually see what's going on. A little bit more space. We have a equals pi times 1 plus I to the power of t. And here we have 1 times, so this whole bottom line is going to be multiplied by 1 plus I to the power of t, which gives us 1 times 1 plus I to the power of t, and when I multiply the fraction by it, the fraction effectively disappears. And we now have exactly what they wanted us to have. I'm going to just restructure it slightly. 1 plus I to the power of t all over 1 plus I to the power of t minus 1 QED. Now, there's lots of different ways you can work that algebra. I think that's the easiest way. Just remembering that when you multiply a fraction above and below the line by the same thing, you change how the fraction looks, but you don't change the actual value of the fraction. You're getting an equivalent fraction. So that's absolutely fine to do. We're used to multiplying both sides of the equals, but that's not going to be as helpful in this particular question.